Welcome to today's explainer. We're going to unlock this chapter on three-dimensional geometry and translate its dense and honestly sometimes intimidating math into a highly visual, easy-to-grasp journey. If you've ever looked at a math textbook and wished you could literally step inside the graphs, well, you are definitely in the right place. So let's just jump right into this chapter with a super practical question. You can easily track a car driving on a flat grid, but what about a flying airplane, or even just a hanging light bulb right above your head? You really can't track those on a flat, two-dimensional piece of paper. So how do we accurately map them? To figure that out, we really have to look at the foundational language of space itself. E.T. Bell once said, "Mathematics is both the queen and the handmaiden of all sciences." And it's the perfect way to frame our chapter today, because these concepts provide the absolute essential scaffolding for physics, engineering, and just understanding the real physical world around us. Here's a quick roadmap for the chapter. We're going to cover the third dimension, axes, planes, and octants, finding your coordinates, the 3D distance formula, proving geometric shapes, and finally, the history of space. All right, section 1, the third dimension. Let's start with the world you already know, and then literally step right off the page. Okay, look around the room you're sitting in right now. Imagine the floor is a standard XY plane, that flat surface you're used to mapping on graph paper. Now, look at the walls. To add the third dimension, we simply need the perpendicular distances from the floor and two adjacent walls. The height of a ceiling fan from the floor, that right there is your z-axis in action. Moving on to section 2. Axes, planes, and octants. Now, let's formalize that room analogy we just talked about. You likely already know all about the 4 quadrants in 2D space. But when we bring in the z-plane, creating the xy, yz, and zx coordinate planes, those intersecting planes actually slice the space into 8 separate parts, and we call these 8 parts octants. Now, what's really fascinating here is how the positive and negative signs completely dictate which of those 8 octants a specific point lives in. If x, y, and z are all positive, you're right there in octant 1. But the moment you start moving left, down, or backward into negative territory, the combination of those plus and minus signs acts kind of like a distinct address code, pinpointing exactly where you've landed in the space. Which brings us to section 3. Finding your coordinates. Let's see how this structure builds our ability to actually plot a specific point. Locating a point boils down to a really simple 3-step procedure. First up, you fix a point on the x-axis. Second, you locate your point in the flat xy plane, just like old times. And third, from that exact spot on the floor, you draw a perpendicular line straight up or straight down to match your z-coordinate. It's honestly a lot like walking to a specific spot on a rug and then just taking an elevator straight up to the exact height you need. All right, section 4, the 3D distance formula, because once you can locate points, you're obviously going to want to measure the exact straight line distance between them. And here's the best part. If you already know the 2D distance formula, upgrading to 3D is insanely intuitive. You literally just add a z. You just take the difference between the z-coordinates, square it, and tuck it right under that same square root alongside x and y. It's such a beautiful logical extension. Next up, section 5, proving geometric shapes. Let's dive into how we can use this exact new formula to prove real geometric shapes exist in 3D space. So we can actually use that distance formula to solve geometric mysteries. For instance, let's test if 3 random points floating out there in space, P, Q, and R, form a perfectly straight line. By running the numbers through the formula, we find the distance for PQ is the square root of 14, QR is 2 root 14, and the total distance for PR is 3 root 14. And boom, mystery solved. Since those 2 smaller segments add up perfectly to the length of the longest segment, 1 root 14 plus 2 root 14 equals exactly 3 root 14, the points definitively lie exactly on a straight line. They are, for sure, collinear. We can do the exact same sort of thing with triangles. Say we've got a triangle ABC, and we want to figure out if it has a right angle. We calculate the squares of the distances of the 3 sides, and let's say we get 686 for side AB, 4571 for BC, and 2709 for CA. Now we just bring in our old friend Pythagoras to verify it. We add the squares of the 2 smaller sides together, 2709 plus 686. Well, that sum definitely does not equal the square of our largest side, 4571.
So because it fails that test, we instantly know that triangle ABC is absolutely not a right-angled triangle. It's a fantastic way to strictly prove geometry without ever having to physically draw it out.
Finally, our last chapter, Section 6, The History of Space. Let's quickly trace how these brilliant ideas actually evolved over time.
Looking at this timeline, you might be surprised to hear that this didn't just happen overnight. René Descartes actually had the initial idea for 3D coordinates way back in 1637, but he never really fully developed it. It took over a century. In 1700, Antoine Parent systematically developed analytical solid geometry, and then, finally, in 1748, the legendary Leonhard Euler fully formalized the 3D coordinate geometry that we still use today.
It's just wild to think about generations of brilliant minds building this mathematical architecture piece by piece. I want to leave you with a really provocative thought from the chapter. Everything we covered in this explainer today built the direct mathematical foundation for Albert Einstein's theory of relativity in the 20th century. Think about that. If this exact math maps out 3D space perfectly, what happens to the math when you add a fourth dimension of time? It really makes you wonder just how deep the rabbit hole of coordinates goes into the space-time continuum, doesn't it? Thanks for joining me for this explainer, and keep exploring.